Okay, so I want to create an adder, specifically an adder that adds two binary numbers that are in the 2's complement form. So here on the left is an example of the 2's complement form. This method of counting includes negative numbers, or, more specifically, negative integers. Okay, so let's suppose I want to add these two numbers that I have here. So then I want to add them. So that actually gives me two sets of data. I get magnitudes, and then I also get sign. So basically, I'm looking at both of these values and I'm taking out their magnitude and I'm taking out their signs. So when I take out their magnitude, I can make a couple of statements here. I can say, oh, and let's suppose that this is number A and then this is number B. So let's look at this case here. What if magnitude of A is greater than magnitude of B? Well, I'm going to say the following. I'm going to say magnitude of A is equal to max. And then I'm also going to say magnitude B equal to min. On the other hand, we have two cases here. We have what if magnitude of A is less than or equal to magnitude of B? Well, in that case, we have two possible outcomes. We have magnitude of A equal to magnitude of B, or we simply have magnitude of A is less than magnitude of B. What about the signs? Well, as far as the signs are concerned, these can only be either 1 or 0. So this is a good starting point to draw out a table. Actually, I should say this the other way around here, so let's fix it. So I should say max, that's going to be a new variable, is equal to magnitude of A, and then I'm going to say min equal to magnitude of B. And then if you notice here, I'm going to say magnitude of A is equal to min. Actually, let's put this. Oh, once again, I did a mistake. Yeah, I want to say minimum is equal to magnitude of A. I'm going to put it right there. And then I want to say max equal to magnitude of B. So let's go ahead and, look at our possible combinations we have here. And then we know that we have two inputs, so we know that I can call it sine of A, and then I can call it sine of B. So this is how I start making my table. And then these arrows go, I guess so that the graph looks nice, or this diagram looks nice. Go all the way down like that. Okay, before we move on, let's just make one thing clear, right? Our signs variable, I guess you could call it, can be 0 or 1, right? So what that means is if the sign is 0, that means we have a positive number. And then if the sign is 1, that means we have a negative number. So we can look here. It's actually clear that this first row, this is our signs variable, or let's call it sign, because each of these values we have here is all negative. So this is what we consider our sign, basically the most significant bit. So anyway, so here I have laid out all the possibilities for these values. So let's look at the first column here on the left. So if magnitude of A is bigger than magnitude of B, then I create these variables max and min, and then I set them accordingly. So max is going to be equal to magnitude of A, and min is going to be equal to magnitude of B. And then I'm going to add them here. I'm creating another variable. I'm calling it sum. And then it's going to be equal to max plus min. And this is a positive value, right? Because we have both zeros here. So we know that the sign is going to be 0 here. So then you follow this same logic for the rest of the table. So, one thing I want to point out here, though, is that there's some similarities that we can take advantage of. For instance, in the cases where both signs are 0, we have this whole row is the same. In the cases where the signs are 1 and 1, so negative, this whole row here is the same. Actually, let me make it a better square here. Like that. And then when in the case when magnitude of A is equal to magnitude of B, well, I can see that this is the only option we have. So what about the case when the signs are different? Well, this one is more interesting. So let's look at some similarities here. So we see that this summation here is actually subtraction because, there's a difference in sign. And so, we're taking the difference. But we see that we have two of the same outcomes here. Right here, I circled it in yellow. So these two are the same outcomes. And then likewise, we have another same outcome here. Like that. So this is what I call, combinational logic. And then from this table, we can actually make some code so that, we consider all cases and have a good adder. So you might be looking at this and you might be saying, well, wait a minute. And the green square that I made in the center, why is that sum equal to 0 and sign equal to 0? Well, the basic reason is that these in this case, both magnitudes are the same, as you can tell by the column. And at the same time, both signs are different. So they have opposite signs. So that means, let's say if you have 8 and the other one has the same magnitude, therefore it's going to have a negative 8, meaning, different signs. So then when you add these two numbers, it basically adds to 0. So that's why in the center, we have a sum is equal to 0 and then sign is equal to 0, obviously, because you can't have a negative 0. So it's just 0. Okay, so I've created the directory already and the project. So I'm going to go ahead and add some files here. So let's go to, I want to add it in the source folder. And then I'm going to name it, let's name it SA for sign adder or signed adder, and then input or to input. And then language, I want to select SystemVerilog. So let's go ahead and start editing this this document here. Okay, so now I have it open here. I'm going to start creating my file here. So I'm going to call it module. And I'm going to define a parameter here. So the default value, I'm going to call it 4. And then I want to declare my input. So that's going to be, because so n is basically n is the number of bits of my input. And then my output, it's going to be, I'm going to call it sum. And that's it. So now I want to do a signal declaration here. Now I'm going to say logic. So these are going to be some internal variables here. So mag sum, and then I'm going to declare this other one, max, the one we were talking about earlier. We have min, mag underscore a, so magnitude of a, and then magnitude of b. How's that? We want our signs also. These are simply 1-bit values. So that's why we don't declare the range likewise with the sum. So now what we want to do is we want to use this function here, always comb. So this basically makes reference to a combinational circuit here. Oh, and let's not forget, we should add here end module in the end. Yeah. Now we have our always combination, and then we can begin this here, and then we end it later here. So then I want to say, I want to first separate out the signs. So I'm going to extract the value of the signs for each of these variables. So that's how I do it. And then I copy this. And I also want this one for B. It's going to be the same thing for variable B. And then what I want to do is I want to separate the magnitude based on the sign value. So let's call this separate. So then I'm going to say, let's see, make this compact. So if the sign is 0, that's a positive number. So I can simply just, say that the magnitude of A is equal to A. So this will give me the actual magnitude of A without the extra bits. And then I say else. Make this look nice. And I'm going to explain what this is doing here. I'm going to finish typing it out. Okay, so yeah. Okay, so this is actually where we deal with the 2's complement. So if we look at my drawings here, let's take a -4 for instance. If we take 4, we see that we have it's represented as 1, 0, 0. And so this is basically, let's say this is our input A. So what I say now is I say, okay, I want to invert all of the bits, right? So then that would give me 0, 1, 1, and then I set magnitude of A equal to that. But then this is not equal to 4 yet. So then what I need to do is I need to just add 1 to it. So what does that give me? That gives me 1, 0, 0. So that's obviously 4. And so that's how I get magnitude from A. And then I get 4 as magnitude. And beforehand, actually the sign, so if I write up here, you know, to the side, sign of A, it looks like an H. This was already saved. So this is already, like, I guess, sort of stored, and that's stored as 1. So the system already knows that this is a negative number and it has magnitude 4. So then obviously I want to do that for both of the A and the B's. So in the case that sign is 1, which is going to trigger this set of lines, and then I'm going to undo the 2's complement. So let's write. And then the same thing here, you know, it undoes the 2's complement. So now what we need to do is we need to sort the largest magnitude as max, and then the smallest magnitude as min. So let's see, I'm going to say if magnitude of A is greater than magnitude of B, well then that's simply going to be max is going to be equal to Okay, and then min is going to be magnitude of b. Okay. However, in any other case, what's going to happen is the following. Magnitude b is going to be the largest. So I'm going to say magnitude b. And then min is going to be magnitude a. So actually, one thing that's important is that this case takes care of the, or I should say, this this includes the case where magnitude of a is equal to magnitude of b. Now what I want to do is I want to perform the addition. Now we get to perform the addition and provide the signs. And to perform this addition, we're going to be basing it on the signs that we have, as well as the magnitudes that we have. Okay, so here it is, and then you can see it that this is it. This performs the addition of basically of the two numbers that are in binary. So the best way to make sense of this piece of code is the following. So if you go back to our table that we made here, we can see that the first if statement takes care of the cases when sign A and sign B are 0, 0 and 1, 1. So we see that when sign A is equal to 0, 0, we see that for all 6 of these cases, we add the max and the min, right? So where is that? So yeah, here it is. For all cases, when these two are either the same or both 0, we add the max and the min. And then if the case when sign is equal to 0, in other words, a positive number, then we set the number to be positive. However, if this number is negative, then we know that the output has to be obviously a negative number. So it's going to be negative, or it's going to be 1 for the sign. And then this one gets a little bit more tricky because there's a little bit of, I guess, cross logic going on here. So we have to consider the case when, let's see, for instance, the case when sign A is 0 and the case when sign B is 1. And at the same time, sign A is equal to, where is it? Okay, yeah, so basically this else if line that we have here is looking at the case when we have, when the summation has to be a difference. So we know that when they have sign A and sign B have different signs, we know that we need to get a difference. So for the yellow box and for the pink box, we see that we have max minus min. So for all 4 of these cases, we know that we have to find the difference of the magnitudes. That's why we have this minus here. But if we want to specify the sign, we have to be a little bit more specific. So that's where this next if line comes in. So let's see if we can make sense of it here. So if we have a basically magnitude A greater than magnitude B, and if it's a positive number, or if magnitude B is less than magnitude B and it's a positive number, then we know that the output is going to be positive. Otherwise, it's going to be 1. Okay, so now we've basically covered all the possible cases for the, we've covered the blue case, the red case, the pink, and the yellow. So the last line we have here is this else statement, and in any other case, we see that the sum and the sign is going to be 0. So basically when the magnitudes are equal to each other and they have opposite signs, obviously we know that they add up to 0. Okay, so now what we want to do is we want to convert back to the 2's complement form. So let's just start. So For any number um, that is a positive integer, we don't need to worry about it because we can just read it as is. But for negative integers, in other words, when the sign sum, this variable is equal to 1, we have to make some statements here. We have to get the summation of the magnitude. And subtract 1 from it. And then what we do is we just invert it. Like that. And then we end this line. And then what we want to do is we want to actually generate the output in the 2's complement form. So we have the sign of the summation as well as the magnitude of the summation. So that should do it. Oh, and actually this is going to be, because we want to concatenate. So this is a curly bracket. And this is also a curly bracket. Okay, so it looks like I got a couple of errors. Okay, right here. Put that to be. Let's save it. And then let's compile. We have one error. Looks like we're missing one end here. Let's save it. Okay, so that works. So now what we want to do is we want to create a test bench. So we want to add to the project, new file. We want to go to the TB folder. And then basically I'm going to call this signed adder 2in underscore TB. Language, obviously, SystemVerilog. Okay, so here we are. I've opened the test bench and I'm gonna, I don't want to bore you with the details, so I'm just gonna paste this test bench. I already made it on the side, so here it is, but I will go over it though. So we see that we declare a timescale. I start the module. Throughout this test bench, I want the parameter event to be equal to 4. So what that means is I'm gonna be instantiating our main code with n bits. So that's where this comes from. That's where this comes in here. So the interesting thing about this is that this SA2in actually has a parameter given for n equals 4, but let's say I instantiate it somewhere, maybe not in the test bench, but maybe in some other file. So what if I instantiate it without any n given to it? So the default is just gonna make it is going to be n equals to 4. So that's basically the default. Okay, so let's move along here. We see that we have 2 test inputs. That makes sense. 2 input signed adder, and then the bits is going to be from 3 to 0, so that's 4 bits. And then we have this flag here because I want to test various things. And then I have the output. So that is actually 4 to 0, so that's 5 bits. That makes sense. I instantiate the 2 input adder, and then I instantiate it with the parameter n, and then unit under tests, and then I relate A to test input, and then B to test input 2, and then sum test out. So since we have 2 inputs, each a binary number, this is going to be our starting numbers here, 0, 0, 0, 1, and then 1, 1, 1, 1, 1, or 1, 1, 1, 1. So what's going to happen here is that flag is set to 0, and so if flag is set to 0, this is going to start looping here, this if statement. And it's going to start looping until you see that the test in rather is less than or equals to test in plus 1. So, and then this one is going to be test in 2 is equal less than or equal less than equal to test input 2 minus 1. So test input is going to be added on. It's going to have added. It's going to continually add to itself by 1. And then test input 2 is going to continually subtract by itself by 1 until test input reaches this value here. At that point, we have this if statement that begins, and then so the flag is going to be declared as 1. We're going to have another delay, and then we're going to reset our inputs, input 1 and input 2, to this binary value here. We have 1, 1, 1, 1, and then 0, 0, 0, 1, and then so on and so forth. So these are basically different, I guess, patterns you could call it, that I'm testing this code here. And the reason I'm so thorough is because I need to make sure that my 2-input adder is working properly, because in the future I might want to use it. I might want to create another code that instantiates from this code to create a 4-input adder, something like that. So yeah, let's see if this works. Okay, so what I do now is I'm going to compile all of this. Compiles nicely. I'm going to go to simulate, start simulation. I'm going to go to work, 2-input Testbench, because I want to simulate that. Okay, looks like it's working. So now I want to look at the flag. I want to look at test input 1, test input 2, and then the output. I want to add that to the waveforms. And then I want to select these 3, and then I want to display them as decimal numbers. Now what I do is and I should change this also, make this 100 milliseconds, that, and I should run it. This doesn't make a difference, because if you look at the test bench, I actually have it stop here, but in case I have a mistake here or something, it's gonna stop at 100 milliseconds, so that's good. So let's go back to our waveforms. I want to look at the full graph here. So there's a lot going on here, so let's just divide this here. So let's put my cursor here and my other cursor here, and then I want to zoom into that selection. So as I go along here, what notice is that we have a test input 1 and test input 2, and what we're actually doing is we're adding these two numbers together, and we're doing so in the 2's complement form. Okay, so as we move along, we have these are all opposite to each other. In other words, the first input is positive, second input is negative, and same magnitude, so it's all zeros. So that makes sense here for this. And then we get to this part here where they're both -8, so that's obviously -16. So it's working good. But as we keep going, now the negative values are in the first input and the positive are in the second input, but still it shouldn't matter. It should still be 0, so on and so forth. And then we have here, and this actually pattern keeps repeating itself for the rest of the the flag here. So when the flag turns 1 or becomes 1, so now it starts with the first input being negative and then the second input being positive. So this is good. This is what we expect to see. So let's go back to the full perspective. Let's look at this second section here. So as we move along here, the flag is 2. So now that's in the third part of our testing phase. So we have -1 and 1, so that's 0. We have 0, 2, that's equal to 2. 1 plus 3 is 4. 2 plus 4 is 6. 3 plus 5 is 8. 4 plus 6 is 10. 5 plus 7 that's 12. 6 minus 8, that's -2. So this is good. This is what we expect to see. Negative plus 7 minus 7, 0. -8 and -6, that's -14. And then we have -5 plus -5, and that's obviously -12. So that's good. Yeah, this seems to be working good. -1 plus 7, that's 6. And then 0 plus -8, -8. Okay, so that works good. Okay, so now I go back to my main code. My main code is working fine, but to be honest, I don't know what this looks like. This is supposed to be a circuit, and it's supposed to be made of logic gates and all these devices, but I don't know what it looks like because it has all of these if statements and else statements. So what we can do is we can open a software called Quartus, and we can actually view how that circuit would look. So let's go ahead and do that. Okay, so I've opened this code in Quartus. I'm using the Prime Lite edition. This is, once again, provided for free by Intel. I want to press Ctrl-K to compile. Takes a while here. Okay, it's undefined. Okay, because I don't have this one defined here. Okay, so of course, so what I want to do is I want to go here in the settings, and then I want to I need to select the file name actually. So it's located here in the source folder. And then I hit apply and I press OK. So now what I can do is I can press Ctrl K to compile. Takes a while. Okay, so that's done. So now what I can do here is I can go to Tools. I can go to Netlist Viewers and then RTL Viewer here. And there it is. This is the schematic for the 2 binary number adder. And right now we see that it's been instantiated as each of these inputs is 4 bits, and then the output is 5 bits here. Maybe you can't see much, so let me zoom in. So here it is. 4 inputs, 4-bit inputs, and then 1 5-bit output. So that's how that works. So you can spend time analyzing this here, but I think what's more important is that you write out this code as simple as possible, and you should get a nice circuit that looks like this.